Here at the 234th American Astronomical Society meeting in St. Louis, Missouri. I'm Rick Fienberg. I'm the press officer of the AAS, and I'm very glad to see all of you here this morning. Assisting me today is AAS Media Fellow Carrie Hensley. She's monitoring our webcast. For those of you who are tuned in remotely, please remember if I sent you the password to log into the text chat so that you can queue up your questions. I'd like to remind you, I forgot to remind you yesterday, to please silence your cell phones or anything else you have that might make noise. I've done mine. There will be one press release going out on the AAS press list this morning. It's for the first presentation. And then I also wanted to mention that if you go to the online press kit, which you can reach from the meeting menu via the press information link, we have uploaded the presentations from yesterday's briefings to the press kit, along with links to the press releases. And the videos from yesterday are on the AAS YouTube channel, and there are links to those from the archived webcast page. So if you missed yesterday's briefing and you'd like to tune in, it's available via video. All right, so the way these briefings work is I'll introduce the topic and all of our speakers, and then I'll turn it over to the first. We'll hear from everybody in succession, and then we'll come back for questions and answers at the end. That way we don't step on anybody's allocated presentation time. So today's briefing is all on the theme of spiral galaxies near and far. We're going to start with the nearest spiral galaxy, the one that we're embedded in, the Milky Way. And then we're going to go and learn more about other galaxies and where spiral structure comes from, how it is generated, sustained, et cetera. And so we have four presentations. The first will be from Darren Dowell from the Jet Propulsion Lab. He'll speak about the spiral magnetic field in the central 5 parsecs, that's roughly 15 light years, of the galaxy, the Milky Way galaxy. He'll be followed by Daniel Kennefick from the University of Arkansas and Mohamed Abdeen, also from the University of Arkansas. They're speaking on two interrelated topics. Daniel's is multi-wavelength study of spiral structure and star formation in disk galaxies. And then Shamir is speaking on new multifaceted evidence in favor of spiral density wave theory. That's the main theory for how spiral structure is formed and sustained. Finally, Patrick Treuthardt from the North Carolina Museum of Natural Sciences will speak on searching for intermediate mass black holes in spiral galaxies with help from citizen scientists. So we will now get started with Darren Dowell from JPL.
Good morning. My name is Darren Dowell from JPL, Jet Propulsion Lab, and I have worked with a team that built an instrument for SOFIA. That instrument is called Hawk Plus, and this same team used that instrument to observe the galactic center, analyze the data, and I'm pleased to show some of the observational outcome from that today. The picture at the top of the screen is the observational team during a SOFIA flight in a panoramic view. All right, so on this slide, we're seeing a view of the nucleus of our galaxy. So on this nuclear scale, roughly 5 parsecs across, there's this bright emission in the infrared from a complex object, which is rotating, but has some characteristics of a disk. So on this nuclear scale, the black hole itself and the radio source associated with it would be just a tiny speck, much smaller than our view. And the entire galaxy is of course, much larger at the 10,000 parsec scale. So here we are just looking at the nucleus. We're seeing emission in the far infrared. In the far infrared, the emission comes from dust. That dust is closely associated with gas, hydrogen and other things. And the gas can be neutral or ionized. The dust can trace them both. So we're seeing several elements in this animation. And by the way, this animation is not an animation in time because the dynamical timescales here are in thousands of years, but we're seeing an animation in wavelengths. So we're seeing progressively longer wavelengths in the far infrared. And one structure that we see across the range here is highlighted by the green ellipse there. That is the so-called circumnuclear ring, which appears to be the inner edge of this disk that's rotating around the black hole. We also see some other streamers of material coming in there. And as we go from short wavelengths, where we tend to see hotter dust, going to longer wavelengths, we see cooler dust. We can see there's something of a sweet spot where we get the sort of the best view of this structure. It's right around 50 microns or so. And as you go to the longest wavelength in the animation, right there at 350 microns, you can see the disk sort of blends in with the environment. That longest wavelength, 350 microns, is the shortest wavelength that we can see from the ground, and even that requires a very high altitude telescope. Everything else requires even higher altitude, so an aircraft, a balloon, or space. If you take all of this far infrared emission and add up the luminosity of it, it's kind of on the small side as galaxies go. It's about 10 to the 7, so 10 million times the luminosity of the sun. So that's only a 0.1% contributor to the galaxy as a whole. Other galaxies have nuclei that might be as bright as the rest of the galaxy itself. But still, this is the most nearby galactic nucleus, so we want to study it to understand the processes and how gas accretes, gathers from the exterior, and finally lands on to black holes. All right, so we chose to observe at 53 microns with this Hawk Plus instrument on SOFIA. We measured the intensity that you see here, but importantly, we also measured polarization, the linear polarization of the light, and that tells us the direction of the magnetic fields in this region. One thing I should tell you before going on to the next slide is the direction of rotation. So this circumnuclear disk is modeled as a tilted ring of material, and it is rotating counterclockwise as we see it on the screen. This is the observational result. So in the color, we see the same far infrared emission that we were looking at on the previous slides, but now with this texture or these streamlines, we've added the observed magnetic field that we see. That comes from the polarization of the 53 micron light. And then superposed on that, we see in the background the stars that are observed with the near-infrared camera on Hubble Space Telescope. You can see that the stars are concentrated toward the center of the image, and in fact, it's that cluster toward the middle which illuminates the dust and heats it and causes it to emit so that we can see it. So we have a nice, pretty spiral pattern to the magnetic field overall, and there were certainly earlier measurements which showed parts of this picture, but for the first time we've got it all in one picture with better sensitivity and resolution of the neutral gas than has been seen before. So let's just go through a few components here. There's a symmetry to the picture. That symmetry is about the supermassive black hole, which is marked with the yellow star in the middle. There is this ring of emission. We can see a symmetric pattern associated with the ring, but it doesn't completely follow the pattern of the ring. And in fact, what we see a lot of is that the magnetic field follows these linear features, these filamentary structures in there. So here's a couple of them highlighted. All right, so it's certainly true in the galactic center region, in the inner few parsecs, it's gravity which dominates the dynamics. So there's more energy expressed in orbital motions than in any of the other terms, any of the other physical effects. And the role of the magnetic field has been a mystery. So we've taken that magnetic field map shown on the previous slide and analyzed some of its properties. And in particular, we're looking at the structure in the angles of the magnetic field and also in the degree of polarization, the fractional polarization that we see. They're telling us the same answer, that the field is relatively strong. So the energy density of the magnetic field is about as strong as the energy density in the turbulent motions. So in other words, the magnetic field can resist the sources of turbulence that are present and channel the gas flow. But gravity still is winning over both of those things. So we're still working through this data toward a publication in the Astrophysical Journal. These are some of the inferences that we're drawing so far. Within this spiral pattern, we see magnetic fields which go all the way from the exterior of the ring, through the ring, into the interior. So these provide channels through which gas can flow into the inner cavity. And also, magnetic fields are sort of two-way streets. Gas can flow out of the region along these same field lines. And the field is relatively strong, so modeling to understand how gas accretes into this region will need to take into effect the strength of the magnetic field. Okay, thank you for your attention.
Well, thank you to the AAS for having me. My name is Dan Kennefick. I'm from the University of Arkansas, and I'm actually speaking on behalf of a collaborator of mine, Ryan Miller, who is the chief author of the work that I'll be describing. Unfortunately, he has been taken ill and asked me to step in on his behalf. So we're also interested in spiral galaxies, in particular, the origins of the spiral structure. The dominant theory is the density wave theory of spiral structure. And while the spiral arms are beautiful, when one gets to the level of theory testing, it's nice to quantify things. And the particular numerical test that we're applying revolves around the pitch angle of the spiral arms in these disk galaxies. And the pitch angle is just a numerical measure of how tightly wound the spiral arms are. It's, in fact, just defined as the angle between two tangent lines, one a tangent drawn to the actual spiral itself, and the other a tangent drawn to a notional circle at the same radius. So the angle will, of course, be 0 if the spiral is a circle and very small if it's close, almost circular. And, of course, it'll be very large if we have a loose spiral where the spiral arm is almost radial in nature. So the spiral arm is a measure of how tightly wound the spiral is. The pitch angle is a measure of how tightly wound the spiral is. Now, an important question in the modern density wave theory is, which is by and large fairly widely accepted, but nevertheless an outstanding question is, are the spiral arms transient or long-lived? Many simulations, models of galaxies suggest that the spiral arms may only last for a rotation or two of the galaxy, but others think that they actually last much longer, maybe up to 10 rotational periods. As I'll describe in a moment, the density wave theory does predict what's called a color gradient across the spiral arms based on the ages of the stars and the other material that's moving through the spiral arms. If the spiral patterns are transient, then this color gradient may not be very consistent even from one part of the arm to the other, whereas if the patterns are much longer lasting, then we'd expect these color gradients to be much more consistent between galaxies and within galaxies. So what is it that's predicted? Well, if we look at a galaxy here in a schematic diagram, the dashed line represents the density wave itself, which has the appearance of a spiral stretching out from the center of the galaxy. Gas and material in the disk is not moving at the same speed that the spiral pattern is. If we think of the spiral pattern as having a constant speed which would maintain its shape as the rotation on goes, then that's the pattern speed. But the speed of the actual gas and dust in the disk will vary with the radius, the distance from the center, as one might expect. That means that the theory predicts that there's something called the co-rotation radius situated somewhere along in the disk, which is the place where the pattern speed of the spiral arm, the density wave, is exactly the same as the speed of the gas and the dust. Away from the co-rotation radius, gas and dust spend some time in the density wave, where it's obviously compressed, that's the nature of the density wave, which may spark off star formation, but then the newborn stars will then presumably drift downstream. And downstream would be ahead of the pattern speed inside the co-rotation radius, but falling behind the pattern, the density wave outside the co-rotation radius. So if these stars continue to form a consistent spiral pattern as they move downstream, then you would actually expect their pitch angle to be smaller, their spiral arm to be tighter than that of the original density wave itself. So what Ryan has done is to take a sample of galaxies, some 30 or so, look at the same galaxy in many different wavelengths to see if the pitch angle is different or the same across those wavelengths. And to summarize his results, we have here that he basically comes across his different measurements of pitch angle with pitch angles that are consistent between some wavebands and then characteristically different with others. So the blue arm here, the deep blue arm here, represents wavelengths at which you might expect to see light coming from the star formation region itself, representative, for instance, of warmed dust, or from stars that are so short-lived that they wouldn't be expected to move very far from where they were born. So that would be the far UV there. So you can see a line labeled 8-micron far UV and H alpha, which would all be wavelengths associated with the star forming region. And then light which would come from actual stars that might have been expected to move out of the star forming region and downstream are seen to have tighter pitch angles, which is suggestive of them having moving downstream from the star formation region. So these results, which are fairly consistent across this sample of galaxies, some 20 or 30, is suggestive of the density wave theory being correct, and also suggestive that the spiral arms might be quite long-lived. Very quickly give you an idea of what the actual data looks like. Each of these plots simply shows pitch angle measurements for each point representing an individual galaxy with its pitch angle measured at 2 different wavelengths. And in the upper case, you see at 2 wavelengths where the pitch angles are comparable because the points are grouped around the line of equality. But in the lower example, you see a case where there's a difference between the pitch angles at these 2 different wavelengths. So the conclusions then, here's a similar for different plots. The conclusion then would be that we do find consistent evidence of a blue to red in the downstream correction color gradient across spiral arms. That is consistent with the prediction of density wave theory and with long-lived spirals. Nevertheless, we should mention that there is a different color gradient from red to blue reported by some groups. And if in the long run we find that there is a discrepancy between certain different kinds of galaxies, then that could be evidence for different mechanisms applying in different galaxies. That's long been suspected, for instance, between grand design spirals versus what are called flocculent spirals. Or it also could be evidence that the picture not being so consistent means that the spiral arms might not be transient after all. So we'll certainly need to do more work in the future. So thank you very much.
Well, thank you, Dr. Kennefick, for setting me the stage. Well, I will also be talking about a topic quite similar to the previous talk. My name is Shamir Abdeen, and I'm from University of Arkansas. I'll be talking about evidence in favor of density wave theory. Now, as you heard from the previous talk, density wave theory depicts the nature of spiral structures in galaxies. The quasi-stationary spiral structure hypothesis demands the existence of a global pattern speed, which in return demands the existence of a co-rotation radius. What's the co-rotation radius? Well, it is the radius in which the velocity of a disk particle would match the velocity of the spiral arm. So if you're on the co-rotation radius, you will be moving with the spiral arm. That's the idea. So in this talk, we'll be focusing on finding the co-rotation radius. The theory also predicts about an age gradient. Now, as you heard from the previous talk, pitch angle is simply a measurement of how tight your spiral arm is. Now, we focused on 4 different wavelengths. We used 3.6 microns, 8 microns, B-band, and FUB. Now, just to remind you, when we are looking at a single galaxy in 4 different wavelengths, we are actually viewing different characteristics of the galaxy. B-band implies newly formed stars, newly formed blue stars. 3.6 refers to old stars. 8 microns for gas and dust lanes. So we are actually viewing different characteristics of the same galaxy. Now, galaxies, they do come in different inclinations. So initially, we had to create a composite image out of those wavelengths, and we deprojected them to a face-on orientation. Once we had that, we started measuring pitch angles. We had 2 different tools of measuring the pitch angles. We had a 2-dimensional fast Fourier transformation method, and we also had a tool called spirality. It's a template fitting approach. Based on these 2 methods, we measured pitch angles for 20 galaxies in 4 different wavelengths. The table over there shows our results, the pitch angles that we measured. Now, once we had our pitch angles, then we started tracing synthetic logarithmic spirals on top of each image, considering the pitch angles as well as their uncertainties. Once we have had those traced, we simply overlaid them one on top of the other to look at places where those traces crossed. Again, this is a very tricky process. Sometimes you do see places where they cross, sometimes you do not see. But based on the places where they do cross, we defined a minimum and a maximum, and we defined the mean location to be the co-rotation radius. Well, how accurate is this? Well, this diagram depicts our 2 methods compared against the mean values obtained from the literature. As you can see, there are error bars as well here. It's quite okay to a certain extent. Now, there are many ways in finding the co-rotation radius. There are more accurate ways. What we say over here is the very fact that we can infer the co-rotation radius from this method implies that we can use this as an evidence in favor of density wave theory. We didn't stop there. We started calculating how long it will take for an object that was born at the density wave to move to its current location on the B-band. So it is a long-lasting question how long these spirals last and whether these measurements are consistent with the star formation theories. And according to our research, our work, it seems it is consistent, and we ended up with a timescale of roughly 50 mega years. So it takes roughly 50 mega years, according to our measurements, considering 6 galaxies and their rotation curves for an object that was born at the density wave to move to its current location in the B-band. So based on this, let me go through the summary. Why is it important to find the co-rotation radius? Well, basically, co-rotation radius has a dynamical influence on the matter and the chemical composition distribution process of the galaxy. So knowing about the co-rotation radius speaks a lot about the galaxy. Well, that's one. But some also claim to have the co-rotation radius associated with a galactic scale habitable zone. So again, it's all a theory, but there are claims as well. In summary, what we have done is we have confirmed the validity of density wave theory through a very direct, simple method using color gradients and simply finding the co-rotation radius, we have shown the validity of the theory. Now, although there are considerable amount of error bars involved, our way is a very simple and a reliable, fast method. Again, the timescales do match. In average, it's around 50 mega years according to our calculations, and they are consistent with the star formation history timescales. Well, that's all. If you have any questions, please feel free to ask at the end. Thank you.
All right. So thank you. My name is Patrick Treuthardt. I'm with the North Carolina Museum of Natural Sciences. What I'm going to do is give you a high-level overview of a project I developed with my collaborators. So the motivation of this is basically every massive galaxy that we've seen seems to have a supermassive black hole in the center, in the nucleus. These black holes range in mass from millions to billions of solar masses. The problem is that the origins of these supermassive black holes is unclear. Some ideas are that they could be seeds, they could be formed from seeds from large gas clouds that collapsed early in the universe. And these could range in hundreds of thousands to millions of solar masses. Another idea is that they form from smaller black holes from some of the first stars that existed in the universe. And so these could range, these initial seeds, or these initial smaller black holes could be hundreds of solar masses. So it's unclear exactly how these initial objects form supermassive black holes in the present-day universe. So the key may be finding intermediate mass black holes. The issue is that these objects are very rare. So there are not many examples of these intermediate mass black holes that have been confirmed so far. There seem to be about a dozen or so that have been confirmed. So they're very few. So what the project takes advantage of is a relationship between nuclear black hole mass and the spiral arm, basically. Thank you, Dan, for mentioning the pitch angle. The quantitative measurement of the spiral arm winding in galaxies, which is the pitch angle. So there's a relationship between black hole mass and pitch angle of galaxies. And what we find is that most galaxies, when you measure the pitch angle, their black hole mass seems to fall in this upper range over here where you get supermassive black holes. And so what we're looking for, or what we want to look for, is black holes at this lower end of the graph right here. So basically with much more open arms and lower nuclear black hole mass. So what we did was we extracted a number of galaxies, about 6,000 galaxies, from a couple of surveys called DECALS and SDSS. And the idea is to, obviously these galaxies, there's a low contrast between the arms and the interarm region, so it's very difficult to really pick out the spiral structure in these galaxies, and it's especially difficult to do it in an automated way. So the idea is to involve the public, so citizens, to identify and trace out the spiral arms in these field galaxies. And essentially what that does is it boosts the signal of the arms, it removes artifacts and noise and any kind of defects in the image, and basically just recreates the spiral structure that you see in a better way. And then what we would do is then essentially throw away the image and just use the combination of all those tracings and measure the spiral arm pitch angle from those tracings. So what we've done is we've developed a project called Spiral Graph that can be found at this website. Unfortunately, it's a long name. And we've developed this on the Zooniverse project builder platform. And this citizen science project was basically developed also mostly by citizen scientists. So this is done mostly by museum volunteers and interns contributing to this project. So essentially, it's just a very simple idea. We show people deep-projected images of galaxies, and we just have them trace out the spiral structure that you see. And this is just an example of that, just a running GIF of that. Some of these are fairly easy. So for instance, this is has a fairly clear spiral structure. Other ones are much more difficult. But essentially what happens is a volunteer is shown an image of a galaxy, they trace out the spiral structure that they see, and then we take the data from the tracings, so from each individual tracing, and then we sum them together. So this is that initial image of the galaxy on the left, and this is the sum of 15 independent tracings done by 15 different volunteers. And you can see in the left image, obviously the contrast in the image is pretty poor, but you can faintly see the spiral structure there. And the image on the right is a combination of 15 tracings, and you can see that it does a very good job of recreating the spiral structure. So where the bright regions are is where agreement is, and the fainter regions are where there's discrepancies, where there are outliers in the tracings. And so what we do then is we take that tracing image and we input it into a program we have called P2DFFT, which is a Fourier transform method of measuring pitch angles, and we get a quantitative measure of pitch angle from that. So what this does is basically this project can be done by anybody. I mean, it's a very, very simple idea. It's a very simple way to do it. We're targeting middle schoolers to older adults just because they have more proficiency with it. What we'll do is we'll provide measurements of, what this project will do is provide measurements of spiral galaxy arm winding and hopefully identify a number of intermediate mass black hole candidates. Once we have a list of candidates, what we want to do is follow up with spectroscopic observations of these candidates to independently confirm the mass of the black hole in the center. And again, doing spectroscopic observations is really time intensive and much more expensive than doing it through the citizen science project, where we just get volunteers to do this. So the citizen science project is a very good first pass of identifying candidates that we can follow up with later. So some secondary implications is that the pitch angles also correlate to different parameters of galaxies as well, such as bulge stellar mass, maximum rotation velocity of the galaxy, and dark matter content. So we can also get information about galaxies in that way as well from these pitch angles. And another implication is that these tracings can serve as training sets for future machine learning programs. So this is something we're also considering from the data that we'll collect from this project. So basically, just to summarize what I've said, we've created a citizen science project. It's called Spiralgraph. We are trying to get volunteers to trace out spiral structure, take those tracings, combine them, measure the pitch angle from those tracings, and hopefully identify a number of intermediate mass black hole candidates using the black hole mass arm winding relationship. And then in the end, what we'll do is we'll take those candidates and follow up with independent measurements to confirm intermediate mass black hole mass. So thank you.
So much news about spirals. I hope you're not dizzy. So we're going to start with questions from here in the audience. The Solar Physics Division's press officer, Trey Winter, is here helping. He's got the microphone. If you have a question, raise your hand and wait for Trey to bring you the mic. Then identify yourself and tell us who you're asking the question of. And then if you're on the webcast, please queue up your questions via the text chat, and Carrie will relate those to us in a few minutes. So, questions for any of the speakers? You must have been so clear. Here we go. No, is this mic on? Sorry, wait a second to get the mic going. No, we're bringing you another one.
How about this? Yes.
Much better.
Susanna Kohler, AAS Nova. A question for Patrick. Is there an understanding of what causes this relationship between the black hole mass and the pitch angle?
Yeah, so my understanding of it is that it's actually a ladder of things that relate the nuclear black hole to the overall spiral structure of the galaxy. And obviously, the radius of influence of the black hole is so tiny relative to the overall structure of the galaxy that there's not a direct relationship. And what it is, there's a relationship between the black hole, something called the shear, around the black hole, which then relates to the bulge of the galaxy, which then relates to the spiral structure.
Any other questions in the room? Got one in the back here.
Daniel Deveau, Canada France Hawaii Telescope. My question is for the first presenter. Do you know the orientation of the disk you see? Because there seems to be some evidence that we're seeing the black hole itself pole on. So do you think it's aligned with it, or is there some misalignment? Or what's the orientation, basically, of the disk? Do you have any idea?
Yes. Well, it sounds like there's multiple alignments or misalignments going on. That circumnuclear ring and circumnuclear disk is inclined by about 25 degrees from what you might expect. You might expect a disk to lie in the plane of the galaxy, and since we're in the plane of the galaxy, we would expect to see a disk edge on, but it is inclined by about 25 degrees. I'm not aware of a good explanation of why that's true. It's fortunate for us because that gives us, a view of the other dimension and lets us map out the structure of it. Relationship with the black hole orientation, I couldn't say. That's definitely beyond me. Yeah.
Okay, down here in the front.
Jim Small, St. Louis Astronomical Society. We're in a barred spiral, so could any of the panel talk about how that formation kind of gets going compared to a regular spiral? And what I assume you could still measure pitch angle and so on for barred spirals as well.
Patrick, do you want to
The formation of barred spirals. So the formation of barred spirals is actually pretty common. I'm not totally clear about your question. Is just how barred spirals are formed? Is that?
Yeah, basically right.
Okay. Yeah. So really the question is because most spiral galaxies that you see in the universe are actually barred spirals in some form. About 3/4 of them, or 66% of them, are barred spirals if you look in the near infrared. So really the question is why aren't there more? Why aren't there barred spirals? Why are some of these non-barred spirals? So really any kind of tug and perturbation in orbits in spiral galaxies will create a bar that's self-sustaining. So it's the non-bards that are actually a little stranger. Yeah.
Yeah, it's probably worth mentioning that computer simulations of galaxies, again, also find it very easy to generate bars. Not that they find it certainly easier to generate the bars than to generate the spirals, as a matter of fact.
Carrie, do we have any online? Okay, we'll go there.
Okay, I have a question for Darren from Monica Young at Sky and Telescope. I realize you're still working through the implications of the strong magnetic field in the inner parsecs of the galaxy, but can you say anything about how this magnetic field could affect the accretion rate for Sagittarius A star, which famously has a very low rate of accretion? Also, there's long been a hunt for millisecond pulsars in the galactic center. Could the strong magnetic field be screening or hiding those pulsars?
Okay.
This is what happens when a PhD becomes a science writer.
Since the second one sounded more difficult, I'm going to try the first one, and maybe you'll all have forgotten about the second one by the time I finish. Well, let's see. I'll be the first to admit that how matter interacts with magnetic fields is pretty complicated, and I'm certainly not a specialist in it. I think at a basic level, our measurements are showing that the magnetic field does need to be taken into account. And it can both assist in accretion of allowing matter to get to the black hole, and it can also repel that. The analogy here is what you might see in the environment of a young star. As material is collecting, it's coming in on orbits, so it's got angular momentum, and the angular momentum as a whole gets conserved. It stays fixed. So things tend to speed up and then zoom past unless there's a method of taking angular momentum from clouds of gas and transferring it to other things like another part of the gas or sending waves down magnetic fields. So these are the kinds of things that have to be addressed by people modeling the galactic center and trying to figure out how material is entering the inside. We know that, as you said, the galactic center, the Milky Way black hole, is extremely inefficient at accretion. As you go from the outside in, you say, look at the amount of material that's crossing through the circumnuclear ring at parsec scales, and then look at the amount of material that must be actually accreting on the black hole, and it's just a tiny fraction of what's available. So there must be some processes happening in the inner few parsecs that are keeping the matter from getting there. It could be things like the fact that there's all those stars producing winds, producing outflowing material. Could be things to do with magnetic fields.
I hate to tell you this, but I remember the second part of the question. Monica was asking also if the magnetic field might be somehow interfering with our ability to detect millisecond pulsars in that inner region of the galaxy.
Well, again, this is pretty far from my expertise, but certainly the magnetic fields do scramble the radio signals in a sense. They can spread out the waves, I guess, in time. If you're studying polarization of the signals, they can change the orientations of it. So it makes it more difficult, but I think the radio astronomers are pretty good at dealing with that kind of thing and sorting it all out by choosing the right wavelength or using multi-wavelength data. That's my best answer.
We'll go with it for now.
Okay.
Any more?
Mm-hmm.
Okay.
Okay, I have a question for Patrick from Catherine Myers at American Institute of Physics. Could you elaborate on why it's difficult to automate the spiral tracing process and why it's easier for humans?
Right. So one of the biggest problems is the low contrast between the arms and the interarm regions. So computers, like computer vision programs, things like that, have a hard time distinguishing between that if the contrast isn't high. Whereas people, like human brains, are really attuned to seeing patterns, even when patterns aren't really there. So it's really easy. It's really easy for people to pick out spiral patterns, and also to see, even to connect discontinuities in spiral patterns. So it basically, whereas machine learning, it's getting better. Computer vision is getting better, but I think it's still not quite as good as the human mind can do. The issue is it takes a lot of time, and so hopefully, with these tracings, we can improve, computer vision programs to actually, improve that and make it more automated so that we don't need people to do it. Yeah.
Just to add something along that lines, even we had the same issue when we were tracing spiral arms. We too used two different independent methods. We used a manual method in which we had the liberty of selecting the pitch angle and the phase angle. So we did that, as well as we did an automated process where the spirals were traced based on the brightest pixels that were available. So again, we had to use those two methods just to make sure we trace the spiral that is there correctly.
Any more online? Okay, we have one here in the front. Martin?
Martin Ratcliffe, freelance on Skyscan. There are a lot of amateur astronomers who are photographing galaxies from their backyard with quite high resolution. But I'm curious about if they wanted to become amateur pitch angle measurers, how would they de-tilt or
De-incline?
de-align the picture. So I was curious what software you use. Do you use Photoshop with a transform mechanism, or is there a Python de-tilt code? What are you using?
The process itself is just very easy, and really all you need to do. I mean, the basic idea is you just you assume that disk galaxies are intrinsically circular. And so all you really need to do is fit an ellipse to the outer faintest parts of the galaxy, and then you rotate the ellipse and then stretch it along the short axis, and that's basically all you're doing. So you can write your own Python code to do that. There's an automated code that works really well called Source Extractor. That's what we use for our project to automate that process to deproject all the galaxies. But I mean, you can just write a short Python script. Yeah.
Yeah, we use IRAF based codes to rotate them and deproject them.
So all of the software is publicly available, including once you've done your deprojection and you want to go on to the measuring the pitch angle, codes like 2D FFT and spirality that we have used are available online if there's anybody who does want to do it. And I think it is a nice aspect of astronomy that it is more open to citizen scientists. That's one reason I'm very excited with Patrick's initiative, and it would be great if people were picking that up.
I'm going to take the moderator's prerogative to ask a few questions, and I'm going to start with one that follows up what we were just talking about. So for Dan and Shamir, you mentioned that your sample sizes were like 30 and 20, roughly. So my first question was, within those samples, did you have a wide range of Hubble spiral classifications, or did you try to stick with a single class of spiral? And then the related question, which is follows up the last one, is then, if you were to do something like what Martin was suggesting, and enlist a corps of astrophotographers or something, to would you be able to sensibly ask for the kinds of data you need? Certain classes of spirals or certain other parameters that you need. Because it seems to me you could probably get a lot more galaxies very quickly if you took advantage of all those images that are out there.
Do you want
Okay. Well, basically, we were looking for clear spiral structures. So if it's a grand design, that would be lovely. So we were mainly hunting for spiral structures with very clear, defined spiral features. So that was one of the main requirements for running 2D FFT, the method that we used to measure the pitch angle. So that constrained our sample.
So you're using galaxies, for example, that do have higher contrast than the ones that Patrick's team is looking at.
Yes,
yeah.
yes.
Okay.
And the inter-arm contrast also plays a major role in selecting our sample.
Mm-hmm.
Yeah.
Okay.
And certainly we were looking for surveys that were, obviously in this case, all professional surveys that had a wide range of image bands available, which would make it harder for the amateur in a backyard observatory to match the sheer range of data. But it's fair to say that many amateurs would be able to provide at least some of these bands. So that's certainly a very interesting way to look at expanding the sample size, because there's no doubt that doing so would be a major step.
Yeah.
And as you say, ideally, in the long run, showing that we could handle a wide variety of different kinds of spirals would be a very important step.
And then I have a question for Darren as well. In the picture you showed of the magnetic field lines and the directions, some of the inner region was colored blue and the disk was colored red, and I wondered if that was just to highlight our identifying those features, or whether those colors had any other significance, like magnetic field strength or polarization or whatever.
Yes, so the colors were based on combining multiple wavelengths in the far infrared. So the bluer colors were shorter wavelengths, and the redder colors were longer wavelengths.
So that was more indicating what was underlying the magnetic field. It didn't relate necessarily to the magnetic field.
Yeah,
Okay.
So that had to do
Okay.
with the temperature of the dust
Okay.
and the gas there.
Okay.
As it turns out, things that were red tend to be dust associated with neutral gas, so neutral hydrogen, molecular hydrogen. And the things in blue were associated with the ionized hydrogen. Those were things that were entering the central cavity and getting heated up enough to ionize the gas.
Okay, and then also, how can you be sure that that the magnetic field is entraining the gas rather than the gas isn't dragging its own magnetic field along with it?
Well, we're actually still trying to sort that out. I think since gravity is strong, it's certainly doing a lot of shaping of the magnetic fields, and a lot of those field lines that we see are following orbital paths, just as a result of gravity. But I guess within those streams, orbiting streams, the field is strong enough to affect motions along the stream and transverse to the stream. So it's having an effect on certainly the smaller scales. And just trying to still sort out in which locations, in which environments, which is the dominant effect that we're looking at.
Okay, my last question is for Patrick. Can you give us a sense, given where the project is at the moment and how it's progressing, when you anticipate doing some of these follow-up observations and when we might start hearing about, the discovery of some additional intermediate mass black holes?
Yeah, so this is still working its way through Zooniverse to become an official project. So it's submitted and it's in review right now, and so we've been in contact with Zooniverse, and so hopefully. Well, right now we also have a retirement for each object of 15 classifications before the object is retired.
Mm-hmm.
So, and we have a sample. Our initial sample is about 6,000 galaxies, and then we're going to move on beyond those 6,000 galaxies. We then plan on moving on to the entire Galaxies Zoo 2 sample of spirals, sorted in a way because they have Galaxies Zoo 2 has flagged those galaxies as qualitatively as these are loose spiral structures, these are tight spiral structures. So we're sorting those based on the qualitative spiral structure, and then we want to measure those as well quantitatively. Mm-hmm. But the initial sample of 6,000 times 15, that's going to take a while. I mean, it's really quick to trace a spiral galaxy, but it's important to get a lot of people to do it. Mm-hmm. So we may have to lessen the retirement criteria in order to move it along. It just depends. So hopefully we'll get some volunteers. We'll get a large number of volunteers and we can push this along. But so each subject set is binned in groups of 1,000. So once 1,000 is done, we're going to download all the data, run it through our code and measure the pitch angles, and then hopefully we'll see if we can pick out one or two if that seems good and maybe start the process. So I don't know. It just depends on how many people are interested and want to take part.
I think in very many cases, at least, when people launch a citizen science project of this sort, they're shocked at how fast they get large numbers of people participating and how many classifications those people will do. It's really quite remarkable, which I think is why citizen science has taken off so much in the last few years. Okay, do we have any more questions here in the room? Anything else accumulated online? Okay, Carrie.
All right, I have another question for Patrick from Catherine Myers at American Institute of Physics. Once a volunteer participates in the project, will they be updated on any new scientific findings that eventually come out of it?
Yeah, that's the plan. So the plan is basically to keep everybody updated with what's going on. So I plan once it's actually really up and running, and it is up and available now, so people can take part, but. I plan at least monthly emails to let people know how things are going, what the progress is, what the state of the project is, things like that. So yeah,
that kind of thing is built into Zooniverse, isn't it? Where there's forums and ways for the project to communicate with the participants.
Absolutely, yeah. The nice thing about the Zooniverse project overall is that each project within Zooniverse has its own set of forums, so you can ask questions. Talk to other people, can ask me questions, things like that. So it's hopefully it's going to be a really collaborative project with the citizens helping out or the volunteers helping out.
And we're seeing more and more instances of papers being published in journals that have citizen scientists as co-authors.
Yeah, and that went to a conference recently, and that was actually it's unclear as to actually how to cite everybody that volunteers, because
Ask the particle physicists.
Yeah, exactly. Yeah. Yeah.
Anything else, Carrie? All right. Well, we're almost at the top of the hour, so I think we'll bring it to a close. I want to thank all the speakers especially, but also the audience, both here and online. And I also wanted to insert a shameless plug that Daniel resisted inserting, which is that if the name Daniel Kennefick is at all familiar, it's because you've been reading very positive book reviews in the science press about No Shadow of a Doubt, his book that just came out on the 100th anniversary of the May 1919 solar eclipse, where Einstein's general theory of relativity first was shown to have some validity. I haven't read it yet, but I'm looking forward to it because I have read so many good reviews, so congrats on that, Dan.
Thank you, Rick.
All right, so this afternoon we'll have another press conference. It's at 3 o'clock here in the same room, 3 o'clock Central. The subject, since we've now had a briefing on the sun and a briefing on spiral galaxies, we have a briefing this afternoon with more sun and more Milky Way. All right, so we'll see you back here at 3 p.m. Thanks again to everybody. Appreciate it.